8th, 1944. 11:30 hours. German observation post, Arromanches-les-Bains, Normandy. Oberleutnant Werner Schmidt commanded a coastal observation position overlooking what had been a quiet French fishing village 3 days earlier. His role was documenting Allied activity and reporting logistics patterns that might indicate offensive intentions. The work required patience and attention to detail, observing shipping movements, counting vehicle types, estimating troop numbers. Schmidt had performed similar duties along various sections of the Atlantic Wall and understood that logistics intelligence often revealed strategic plans before tactical movements made them obvious. The Allied invasion had occurred on June 6th, less than 48 hours earlier. Schmidt's position had survived the initial bombardment, though German forces had withdrawn from the immediate coastal area under overwhelming Allied pressure. His observations documented what appeared to be a conventional beach landing, troops coming ashore from landing craft, vehicles struggling through sand, supplies being stockpiled in vulnerable positions above the tide line. The scene matched German intelligence predictions about Allied logistics challenges. Without captured port facilities, the Allied forces would struggle to sustain operations beyond the initial beachhead. Then Schmidt noticed something that made no sense. Through his observation telescope, he saw vessels offshore that weren't warships or transports, but massive rectangular structures being maneuvered into position. Each structure was perhaps 60 meters long and 15 meters high, far too large to be conventional maritime equipment. As he watched, several of these structures were deliberately flooded and settled onto the seabed in precise alignment, creating what appeared to be a breakwater extending hundreds of meters from shore. He reported this observation to his headquarters, describing the structures as possible defensive obstacles or perhaps some type of anti-submarine barrier. The response instructed him to continue observing and provide more detailed intelligence. Over the following hours, Schmidt documented additional vessels arriving with more rectangular structures, with floating roadway sections, with pier components that were being assembled into what was unmistakably becoming a harbor. By afternoon, Schmidt's reports reflected growing disbelief at what he was witnessing. The British were constructing a functional deep-water port on an open beach, not merely a temporary landing facility, but an actual harbor with breakwaters, piers, and floating roadways capable of allowing ships to dock and discharge cargo directly onto transport vehicles. The construction was proceeding with speed that seemed impossible. Structures that should require months of work were being installed in hours through what appeared to be prefabricated components designed specifically for rapid assembly. His report to division headquarters stated, "British forces are constructing what appears to be a complete harbor facility at Arromanches. Large concrete structures have been positioned as breakwaters. Floating piers are being assembled. Roadways are being connected from ships to shore. If this construction continues at current pace, the British will possess a major port facility within days. Request assessment of whether this construction represents threat to German defensive planning." The response came hours later and reflected confusion at higher command levels. German intelligence had no information suggesting the British possessed capability to construct harbors at sea. The structures Schmidt described didn't match any known Allied equipment. The speed of construction seemed incompatible with normal engineering timelines. Yet Schmidt's observations were being corroborated by other coastal observers reporting similar construction at different beach locations. Something unprecedented was occurring, and German command struggled to understand its implications. The strategic problem that demanded the impossible. Allied planning for the invasion of France confronted a fundamental logistical reality. Modern mechanized armies consumed supplies at rates that exceeded what could be sustained through beach landings. An infantry division required approximately 600 tons of supplies daily. An armored division needed substantially more. The initial invasion would put multiple divisions ashore, all requiring continuous supply streams of ammunition, fuel, food, and equipment. Without port facilities capable of handling this logistics burden, the invasion would stall within weeks, regardless of tactical successes. The French Channel coast offered several major ports, Cherbourg, Le Havre, Dieppe, but German forces held all of them and had fortified them extensively. Allied intelligence assessments concluded that capturing these ports would require sustained operations that might take months. Even after capture, German demolition would render them unusable for additional months, while engineers cleared wreckage and restored facilities. The timeline was unacceptable. Allied forces needed immediate port capacity beginning on the invasion's first days, not months later after prolonged siege operations. The solution required capability that didn't exist in any military's inventory: the ability to create port facilities where none existed, on open beaches, under combat conditions, using equipment that could be transported across the English Channel. The concept seemed to violate basic engineering principles. Ports required years of construction, specialized equipment, protected harbors, massive investment of materials and labor. Building them in days on hostile shores appeared impossible. British engineering assessment concluded that the impossible could become possible through systematic decomposition of the problem. A port wasn't a single entity, but a collection of components: breakwaters to protect against waves, piers to allow ships to dock, roadways to move cargo from ships to shore, anchoring systems to keep everything positioned correctly. If each component could be prefabricated in Britain, transported across the Channel, and assembled rapidly at the invasion beaches, then the impossible port could become operational reality. The Mulberry Harbour concept emerged from this analysis in 1943. British engineers would design and construct portable harbour components in Britain using existing industrial capacity. The components would be towed across the Channel immediately following the invasion. Engineers would assemble them on the beaches to create functional harbours capable of handling the logistics demands of multiple divisions. The entire system would be operational within days of the invasion, fast enough to sustain operations before logistics shortages could cripple the offensive. The engineering challenges were extraordinary. The components had to be large enough to create functional harbour facilities, but small enough to be towed across the Channel. They had to be strong enough to survive Atlantic storms, but light enough to float during transport. They had to be designed for rapid assembly by personnel working under combat conditions with limited heavy equipment. The entire concept required solving technical problems that conventional harbour engineering had never confronted, because conventional harbours weren't built under these constraints. Engineering the components. The Mulberry Harbour system consisted of multiple component types, each designed to perform specific functions while meeting the constraints of transportability and rapid assembly. British engineering teams worked throughout 1943 and early 1944, developing, testing, and manufacturing these components using Britain's strained but still substantial industrial capacity. The Phoenix caissons represented the system's foundation, massive concrete structures that would serve as breakwaters protecting the harbour from wave action. Each Phoenix was approximately 60 meters long, 15 meters wide, and 15 meters high. The walls were reinforced concrete over a meter thick. Internal compartments could be flooded to sink the caisson into position or pumped out to float it during transport. The largest Phoenix units displaced 6,000 tons, comparable to destroyers. Manufacturing them required purpose-built construction yards and consumed enormous quantities of concrete and steel reinforcement. British industry constructed over 200 Phoenix caissons at sites around the British coast. Some construction occurred in conventional shipyards, but the demand exceeded available capacity. Engineers established temporary construction sites in river estuaries, behind coastal breakwaters, even in farmers' fields that could be flooded after construction to float the completed caissons. The entire British construction industry contributed: concrete suppliers, steel manufacturers, construction crews, marine engineers. The mobilization represented Britain's industrial capacity being applied to a single project with intensity that diverted resources from other critical war production. The whale floating roadways provided the means for vehicles to move from ships to shore. Each whale section consisted of a steel deck supported by pontoons that floated at water surface. The sections connected to form continuous roadways extending from deep water to the beach. Telescoping legs could extend to the seabed to stabilize sections, while flexible joints allowed the roadway to rise and fall with tides without breaking. A complete whale roadway could stretch nearly a mile from shore to deep water, providing multiple traffic lanes wide enough for tanks and heavy trucks. The spud piers served as the junction between floating roadways and moored ships. Each pier consisted of a platform supported by steel legs that could be raised or lowered using hydraulic systems. As tides changed, the pier adjusted height to maintain level connection with the whale roadways, while ships docked alongside could load and unload continuously. The engineering complexity was substantial. The piers had to support heavy loads while remaining mobile enough to adjust with changing water levels. The bombardon floating breakwater units provided additional wave protection beyond what the Phoenix caissons supplied. These were cruciform steel structures that floated at the surface, connected in long chains to create barriers that reduced wave energy before it reached the inner harbor. Each bombardon was over 60 meters long and weighed 200 tons. They represented simpler construction than the Phoenix caissons, but still required substantial manufacturing capacity and careful design to ensure they could survive channel towing and perform effectively in Norman weather conditions. The crossing. The transportation of Mulberry components across the English Channel represented one of the largest maritime construction operations ever attempted. Beginning on June 6th and continuing for days afterward, hundreds of vessels towed the massive components from British ports to Normandy beaches. The operation required precise coordination, favorable weather, and substantial luck to succeed without catastrophic losses. The Phoenix caissons were the most challenging to transport. Each caisson was too large to be towed by a single vessel. Multiple tugboats worked together, maintaining exact speeds and headings to prevent the tow cables from parting under strain. The crossing took approximately 18 hours under ideal conditions, but weather delays and mechanical problems extended many journeys substantially. Each caisson's loss would create gaps in the planned breakwater system that might compromise the harbor's effectiveness, so the transportation was planned with redundancy that allowed for some losses while still providing functional harbor capacity. The towing convoys moved at approximately 3 knots, walking speed. This made them vulnerable to German U-boats, surface raiders, and aircraft. Allied naval forces provided protection, but the convoys represented lucrative targets if German forces could locate them. British planners routed the convoys along paths that air cover could protect continuously and that Allied naval forces could defend against submarine attack. The defensive effort consumed substantial military resources that might otherwise have supported combat operations. Several components were lost during the crossing. Tow cables parted in rough seas, setting caissons adrift until they could be recovered. Some whale sections broke free and had to be abandoned. A few bombardons sank during the crossing when structural weaknesses caused flooding. The losses were within planning margins. British engineers had manufactured surplus components specifically to ensure that transportation losses wouldn't prevent the harbours from becoming operational. This redundancy represented additional manufacturing burden, but proved essential when actual losses matched pessimistic planning assumptions. The German response to these convoys was confused and ineffective. Luftwaffe reconnaissance observed massive maritime traffic, but couldn't determine what the unusual structures being towed represented. U-boat commanders reported large, unidentified objects in channel waters, but couldn't get clear enough observations to assess their purpose. German surface forces were largely bottled up in port by Allied naval superiority and couldn't investigate the mysterious convoys. By the time German intelligence understood what was being transported, the components were already arriving at Normandy beaches and assembly was beginning. Assembly under fire. The installation of Mulberry components began on June 7th, 36 hours after the initial invasion landings. British engineers and Royal Navy personnel worked on open beaches, while German artillery still ranged the area. German aircraft occasionally attacked, and the tactical situation remained fluid. The assembly had to proceed, regardless of these hazards, because every day's delay in making the harbours operational increased the risk that logistic shortfalls would cripple the invasion. The first components installed were the block ships, old vessels deliberately sunk in precise positions to create initial breakwaters that provided some protection for the inner harbour components. Royal Navy crews sailed these vessels across the channel, knowing they would scuttle them upon arrival. The ships ranged from obsolete battleships to worn-out merchant vessels, anything large enough to create obstacles to wave action. The crews positioned each vessel carefully, then opened seacocks to flood the hull in exactly the right location. Within hours, the sunken vessels created barriers that reduced wave heights in the areas where Phoenix caissons would be installed. The Phoenix installation required extraordinary precision. Each caisson had to be positioned correctly, flooded at the right rate to settle onto the seabed level, and properly aligned with adjacent caissons, and verified stable before the next component was positioned. The work occurred in tidal waters, where conditions changed every 6 hours, requiring engineers to calculate flooding rates that accounted for changing water depths. German artillery fire occasionally landed among the working parties, forcing temporary halts while personnel took cover. Some caissons were damaged during installation when unexpected conditions caused settling errors, requiring engineering improvisation to maintain the breakwater's integrity. The whale roadways required assembling while floating, then positioning the completed assemblies to connect with shore installations and spud piers. The flexible joints that allowed the roadways to adjust to tidal changes had to be installed correctly, or the entire roadway could fail under the stress of heavy vehicle traffic. Engineers worked continuously, often for stretches exceeding 30 hours, to complete critical connections before tidal changes would make the work impossible until the next favorable period. Within 4 days of beginning installation, Mulberry B at Arromanches was handling cargo. The initial capacity was limited. Single ships could dock, unload, and depart, but the system worked. Over the following week, additional components were installed, capacity increased, and the harbour evolved from experimental facility to critical logistics hub that sustained entire armies. The storm that proved British engineering. On June 19th, a severe storm struck the Normandy coast with winds exceeding 40 knots and waves that reached heights dangerous even for large vessels. The storm lasted 3 days and represented the worst channel weather in decades for that time of year. Allied shipping operations halted completely. Beach operations became impossible. The invasion's logistics pipelines stopped flowing, creating the exact supply crisis that Mulberry Harbors were designed to prevent. Mulberry A, the American-built harbor at Omaha Beach, suffered catastrophic damage. The breakwaters failed, allowing full-wave action to strike the inner harbor components. Whale roadways broke apart under the stress. Spud piers were torn from their moorings. Ships that couldn't evacuate in time were driven ashore and wrecked. Within 48 hours, Mulberry A was essentially destroyed. American forces would have to rely on beach landings and the eventual capture of Cherbourg for logistics support rather than having an operational harbor at Omaha. Mulberry B at Arromanches survived with moderate damage. The Phoenix breakwaters held their positions despite wave action that should have displaced them. The whale roadways flexed with the waves but maintained structural integrity. The spud piers adjusted with the changing water levels and continued functioning. Some components were damaged and required repair, but the harbor remained operational throughout the storm and resumed full operations immediately after weather improved. The survival of Mulberry B validated British engineering decisions that had been controversial during design. British engineers had insisted on stronger caissons, more robust anchoring systems, and more flexible roadway connections than American engineers believed necessary. The additional engineering complexity and cost had generated debates about whether the enhanced designs were justified. The storm provided definitive answer. The enhanced British specifications were exactly what was needed to survive the worst weather the Channel could produce. German observers, watching the storm damage, understood that they'd missed a critical opportunity. If the storm had occurred days earlier, before the Mulberry Harbors were fully operational, it might have created supply crisis that could have stalled the invasion. Instead, the storm occurred after British forces had established logistics capacity sufficient to sustain operations even through several days of reduced supply flow. The timing represented another element of Allied fortune that contributed to invasion success beyond what planning and preparation alone could guarantee. What the Germans admitted. German post-war assessments acknowledged that Mulberry represented British capability that had surprised and impressed them. The technical achievement of constructing functional harbors on open beaches within days of an invasion exceeded what German engineering considered possible. The strategic impact of having assured logistics capacity from the invasion's start eliminated defensive advantages that German planning had counted on. Oberleutnant Werner Schmidt, whose observations had documented Mulberry B's construction, was captured in August 1944 and interrogated about German intelligence failures regarding the invasion. His assessment was frank. "We knew the British were excellent engineers. We didn't imagine they would build transportable harbors and install them on invasion beaches under combat conditions. Our defensive strategy assumed Allied forces would need weeks to establish adequate logistics. The artificial harbors eliminated that vulnerability. By the time we understood what they'd built, it was too late. Their logistics were already functioning well enough to sustain operations indefinitely." A German engineering officer who examined Mulberry components after the war stated, "The British harbour construction represents impressive technical achievement. The components are well designed for their purpose. The installation procedures were clearly planned in detail. The entire system demonstrates industrial capacity to manufacture complex equipment at scale, and organizational capability to employ it effectively under difficult conditions. Germany possessed neither the industrial capacity nor the operational flexibility to create similar systems during the period when they might have been strategically valuable. The cumulative German testimony acknowledged that Mulberry represented the kind of operational surprise that couldn't be countered through tactical adjustments. German forces could damage individual components, could shell the harbors, could attempt air attacks, but they couldn't eliminate the fundamental capability the harbors provided, assured logistics capacity that sustained Allied operations regardless of German efforts to disrupt them. That capability, established within days of the invasion, ensured that German defensive strategy based on denying ports would fail, regardless of how well German forces fought tactically. The Germans had expected to face an invasion constrained by logistics limitations that would create operational vulnerabilities German forces could exploit. Instead, they faced invasions supported by logistics infrastructure that functioned from day one, because British engineers had built harbors from nothing on open beaches under fire. That difference between what German planning anticipated and what actually occurred shaped the entire campaign and contributed substantially to Allied success. The harbors built from nothing proved that British engineering could achieve the impossible when strategic necessity demanded it. The massive concrete caissons, the floating roadways, the adjustable piers, all of it worked exactly as designed, despite being employed in conditions more severe than testing could simulate. The engineers who made it work demonstrated that technical competence combined with determination could overcome obstacles that appeared insurmountable. Mulberry harbors were temporary. They operated for only months before conventional ports made them unnecessary. But they were decisive. They provided logistics capacity at exactly the moment when it was needed most, ensuring that the invasion could succeed despite the enormous supply demands of modern mechanized warfare. That achievement, built from nothing on hostile shores under enemy fire, represented British engineering at its most effective, solving impossible problems through systematic analysis, creative design, and determined execution.